Okay, so now let's talk about the model and how to solve that model. Again, mathematics are not the most important thing for us to get ideas, but they are required because only through mathematical models and the analysis we can understand and we can deliver a useful message from that model. Okay, let's start. So we're going to consider a manufacturer and a retailer in an indirect channel. The product is perishable and there is just a single period of demand. That demand, of course, is random. Production is under make to order, and that basically means the manufacturer does not face demand uncertainty. The manufacturer only need to get ordered and then make the production. However, the retailer is a news vendor. That means the retailer must prepare the inventory before the selling season starts. We're going to use the following notations in this video. The notations are a little bit different from the paper, but there is a one-to-one mapping, so you should have no difficulty to understand the paper. First is the unit production cost, which you see. Unit wholesale price will be W. Unit return credit and percentage of allowable return are small r and capital R. The retailer is going to choose an order quantity capital Q, and the demand, the random demand, has capital F and small f as the distribution and the density functions. We're going to assume the following basic assumptions. The wholesale price must be within small c and small p, so it cannot be lower than the production cost and it will not be greater than the unit retail price. The return credit will be smaller than W. Okay, so if I sell you product at $10, I am not going to allow you to return at $11. If R is greater than W, then the retailer will not try to sell anything. Small f is continuous, and it must be the demand must be non-negative. Okay, these are just some technical assumptions for us to do the derivations. So, as you know, the game starts from the manufacturer side. The manufacturer is going to offer a contract, and then the retailer makes the order decision. So, the retailer has observed the announced return contract WR and capital R, and then the retailer must formulate his own expected profit like this. In any case, I need to pay this amount as my purchasing cost, and then according to my sales quantity, I'm going to earn some money. Okay, so what are them? My sales revenue can be found here. Okay, those terms that are multiplied with the retail price P. At the same time, I may also earn some money by returning my products, my unsold products, to the manufacturer. Those are obtained with these small r terms. Okay, so we have here, here, and here as the sales revenue, and here as the return credits. So, in general, what we may have are three situations. So let me try to write it down. Okay, so let's say this is the possible demand. As a retailer, I may order at this level, okay, and then the demand may be either larger than my order quantity, or the demand may be lower than my order quantity. If the demand is greater than the order quantity, then I'm going to sell everything, and the sales quantity will be capital Q. So I will earn this amount with probabilities for demand to be greater than capital Q. Okay, so this is the case in region 3. How about the case that demand is less than quantity? in that case, we need to distinguish between two cases. So one critical quantity is 1 minus R times Q. Okay, this is because the manufacturer may not allow the retailer to return everything. Let's say if capital R is just 1/2, okay, then if you order 1,000 units, you are only allowed to return 500 units. So when I have this capital R, I know if I sell too much, if I sell a lot, then those remaining products can be returned. Otherwise, I cannot return everything. Okay, so let's read this formula. Let's consider region 1 first. In region 1, what happened? I only sell less than this quantity. Okay, I only sell less than this quantity. For each unit I sell, I earn small p as my profit, sales revenue. Okay, and then I cannot return everything. I can only return this amount. Okay, how much is it? Is R times Q. Okay, it's R times Q. So I have a lot of leftover, but I am only allowed to return R times Q because this is the maximum allowed return specified with this parameter capital R. For region 2, that's another story. If I sell more than 1 minus R times Q, but less than capital Q, then I'm going to again earn some sales revenue. But now, my return quantity will just be all my leftover, which is Q minus my demand. So this is my second region, expected revenue. And of course, this is the first region. So depending on different demand realization, I can write down what will be my expected revenue. And collecting everything is going to give me the retailer's total profit, total expected profit under an order quantity. For the manufacturer's expected profit is somewhat similar or just at the opposite side. The manufacturer needs to pay CQ as the production cost, and the manufacturer can earn Q times W as the wholesale revenue. But the manufacturer is also facing some risks about buying back the unsold products. This, of course, is what happened when the demand is very small. When the demand is very low or very small, the manufacturer is going to take capital R times capital Q back. Or if the demand is somewhat moderate, then the manufacturer only need to take back Q minus X, and X is the demand. Finally, if you sum the two terms up, you can see that the expected sales profit is just a very basic news vendor problem profit. Okay? You won't see small r, small w, and capital R because they are something that affect the interaction between the manufacturer and the retailer. So R and W, they are internal parameters inside the system. From outside the system, no one really cares about or no one really sees these three parameters. So from outside of the system, for example, from the consumer's perspective, consumers only care about the order quantity or the inventory level, and that inventory level is going to determine the system profit. It's just one news vendor profit function. So the timing, let me try to review the timing for you. First, they will sign a return contract. In this study, we do not specify how this return contract is determined. Okay, we do not assume it is the manufacturer's decision or the retailer's decision or who makes the decision. We just allow all the possibilities to occur. And we want to ask whether there is any return contract that can induce efficient order quantity. So we're going to assume at the first stage a return contract is signed, and then the retailer must decide an order quantity, and then the manufacturer will make the production and deliver the products to the retailer. The retailer then sells to the uncertain demand after the demand is realized. And if there is any unsold product, the allowed unsold products will be returned to the manufacturer. That's the timeline of this problem. So now it's time to try to solve this problem. Again, we start with the benchmark, which is just the system optimal inventory level. As you are already familiar with that, the system optimal inventory level is just this guy. Okay? If Qt star is the optimal inventory level, it will satisfy this equation, this news vendor equation. This is based on the demand function, and the right hand side is just the critical ratio. And what we are looking at is whether there is a return contract that can make the retailer order Qt star. Of course, we already know if W is the only parameter, then the retailer will never order Qt star. The retailer will order less than that. So we want to ask whether capital R and small r can induce the efficient result. So let's look at the retailer's problem. The retailer's expected profit is this one, right? So in order to find the optimal decision, the retailer must differentiate his profit function with respect to capital Q. So this takes some mathematical training. We need to apply the Leibniz integral rule. Okay, actually you have used that when you are dealing with the very basic news vendor problem. But here, the problem is slightly more complicated, so let me try to help you refresh your memory. Suppose f of xy is a function such that the partial derivative with respect to y exists and is continuous. Okay, these are just some technical assumptions, and we're going to assume they are true. Then, how may we find the differentiation of the integral of f? We have this formula. So let me use this pi of q as an example. Let's look at this particular integral. Okay, what I am doing is that for this particular function, I have an integrand here. Okay, this is my integrand for this integral, and you can see that there is x. Okay, x is here, and also there is capital Q. Okay, capital Q is the variable that we are going to differentiate upon. So capital Q is the y variable here, and x of course is x here. Okay, you can see we are integrating the integral with respect to x, and then we will differentiate the result with respect to y or q. Here, one thing to keep in mind is this q also appear at the upper bound or lower bound of an integral, just like the upper bound and the lower bound of this integral may be a function of y. Okay, and then we have the formula here. Basically, all we need to do is first plug in the upper bound to the function, get the result, and then just like the chain rule, multiply the outcome of differentiating the upper bound with respect to y, and then minus the plug-in of lower bound, and then multiply the lower bound differentiated with respect to y. And then finally, the last term is to keep the original integral, but differentiate the integrand with respect to y. If we sum these three terms together, we get the result. Let's try to do this. So the rule is here. We know that the retailer's expected profit has four terms. 1, 2, 3, 4. Okay? For the first term, differentiate this term with respect to q is easy. Okay, we just get this one. For the second term, okay, q is here, and we have this is an upper bound, this is the lower bound. So the first term is to plug in the upper bound to small x. Okay, let me write it down. Small x is here, small x is here. Okay, I need to plug in the upper bound to the variable x, to the dummy variable x. So 1 minus r times q goes to here and here. Okay, so 1 minus r goes to here, 1 minus r times q goes to here and here. One thing to keep in mind is that after that, I also need to differentiate the upper bound with respect to y. So I need to differentiate this with respect to q. That's why I get 1 minus r. Okay, that's why I get 1 minus r. So that's the first term. For the second term, there is nothing because 0 differentiated by q. This term is just 0, so I don't have the second term. For the last term, I will keep the original lower bound and upper bound, and then differentiate the integrand by capital Q. So that's why I only leave this term there, r, and f of x. Okay, this is how I get the differentiation of the second term to this. I can repeat this process with this term and this term to get da 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 da. But you may want to do this verification by yourself, and then I will move on. So by collecting everything we just did in the previous slides, and after some combinations, we can collectively get this particular formula as our result. Okay, if I differentiate pi r by q, I get this. Okay, so now you know learning calculus is useful. If you don't have that particular technique, you just cannot get this result. Okay, so with this, of course, we know that the retailer should choose a quantity to satisfy this particular thing equals 0. Okay, that's my first order condition. The retailer should choose a quantity that make the first order derivative 0. Okay, so numerically or when function is attractable, we can find q to satisfy this equals 0. That's the retailer's ordering strategy. What you should do before that is to make sure that first, pi r of q should be concave, right? So you probably want to verify the second order derivative of this particular function. Okay, now differentiate this again with respect to capital Q to see whether the second order derivative is really negative. That can be done. And also, with that in mind, you can make sure that there is a unique root. So you will be able to find a q to satisfy this equation. And that can also be done. So we're going to minimize the amount of mathematics. So let's skip them. Just convince yourself that this can be done. And then what we want to do is to compare the system optimal order quantity with the retailer optimal order quantity. We hope that if we plug in the system optimal order quantity to the retailer's first order condition, we hope that it can be satisfied. Okay? If Qt star is just satisfying the retailer's first order condition, then it's perfect. It means the retailer is going to feel that the system optimal order quantity is also optimal to himself. And then the retailer will order the system optimal quantity. So we know this is the function, right? And we ask whether plugging in Qt star can make it 0. One thing we know is that f of Qt star must satisfy this. Okay? If it is system optimal, f of Qt star must be p minus c over p. So p minus c over p can be placed into the first order condition. So now our question has been reduced to the following. We want to ask whether there is any WR and capital R so that this particular equation is satisfied. Okay? We want to ask whether such WRR exists or not. And if it exists, what are some properties that we may say about it? Okay? So that will be our task in the next video. Thank you.